Aircraft carriers have played a major role for the United States Navy and maritime warfare history. Many people visualize aircraft carriers as floating cities. The aircraft carrier weighs more than 100,000 tons and serves as a seagoing airbase that's equipped with a full-length flight deck. Aircraft carriers can house up to 6,000 crew members and sailors on board, approximately 100 fighter jets that are well worth over about $30 million each, as well as various other luxury facilities you'd find in a city. Typically, it's the capital ship of a fleet, as it allows a naval force to project its air dominance all over the world. When you think about the size of the largest aircraft carriers in the world, like the USS Gerald R. Ford and the Nimitz-class carriers, it's fair to say that you'd not immediately think of these 400-meter-long battle monsters to be maneuvering and drifting on the water. However, the reality is far from that. These carriers are capable of executing truly incredible and extreme maneuvers at speeds of up to 35 miles per hour. But how does the USS Gerald R. Ford succeed in making these turns despite her sheer size? Well, to answer that question, we'd have to dive into the specifications of the USS Gerald R. Ford. This classification of supercarriers is the latest class of carriers developed by the United States. They're set to replace the current fleet one by one. It's reported that 10 carriers are going to be built and launched over the upgrade process. It's expected that all 10 carriers will be ready with combat capabilities by 2040. The Gerald R. Ford class has a load displacement of 100,000 tons and has a complement of 508 officers and 3,789 enlisted men. The first carrier in the class, the USS Gerald R. Ford CVN-78, was delivered to the U.S. Navy in May of 2017. It was officially deployed for duty on July 2017 and achieved initial operational capability in December of 2021. The carrier features a 337-meter flight deck with a 78-meter beam, just slightly larger than the Fujin, and was equipped with an electromagnetic aircraft launch system and advanced arresting gear. The carrier can store more than 75 aircraft and house more than 4,500 crew members, which include personnel, the ship's company, the air wing, and other support staff. The Gerald R. Ford class carrier is powered by two A-1B nuclear reactors. These nuclear reactors provide the aircraft with an unlimited range. The ship utilizes 4 electromagnetic catapults and an advanced system of arresting gear. The air wing employed on CVN-78 consists of 4 Super Hornet squadrons, an E-2 Hawkeye squadron, an EA-18 Growler squadron, C-2A Greyhound squadron, and 2 MH-60 helicopter squadrons. Currently, there are no 5th-generation F-35 Lightning II fighters attached to the air wing, but it's expected to be added into the near future. The F-18 Super Hornet is a supersonic twin-engine multi-role fighter and is considered as a 4th-generation fighter, putting it in the same class as the J-15B. The F-18 Super Hornet can accommodate 1 to 2 crew members depending on the variant and the mission type. It has a length of 18.31 meters and a wingspan of 1.62 meters. Its empty weight is about 32,000 pounds, and its max takeoff weight is 66,000 pounds. The aircraft has the capability to reach insane speeds up to Mach 1.6, which is allowed due to the 2 General Electric F414 TAC 400 afterburning turbofans powering it. Each of these engines produces up to 22,000 pounds of thrust with afterburners lit. It has a range of 1,458 miles and a combat range of about 511 miles. The weapon loadout is multi-purpose and can be easily configured, but can include one 20mm M61A2 Vulcan cannon and around 400 rounds of ammunition. It can also carry 4 AIM-7 Sparrow missiles, 4 AIM-9 Sidewinder missiles, and 12 AIM-260 Jota missiles. It can also be configured to carry 6 AGM TAC-65E or F variant Maverick air-to-ground missiles, 6 AGM-8 HARM missiles, 4 AGM-158 JASA missiles, 4 AGM-154 Joint Standoff Weapon or JSOW glide bombs, 4 AGM-84 Harpoon anti-ship missiles, 4 AGM TAC-158C LRASM missiles, laser-guided bombs, Mark 80 series bombs, CBU-78 Gator mine systems, You get the idea. Moving on to the Nimitz-class carrier, which is the world's second largest aircraft carrier classification. The first carrier in this class started its duty in May of 1975. Each carrier of the Nimitz class was specially designed to serve and operate for 50 years and only required one midlife overhaul. The 332-meter-long supercarrier features a massive flight deck that measures about 4.5 acres. The deck is capable of storing and carrying 60 or more aircraft. Each ship towers at a staggering 20 stories above the water. The carrier can accommodate 3,200 ships company, 1,500 members in its air wing, and 500 other crew members at a time. The Nimitz class is fueled by 2 nuclear reactors, providing a maximum speed of more than 30 knots. 20mm Phalanx CIWS missile defense cannons, rams, and NATO REM-7 Sea Sparrow missile launchers for anti-ship and anti-aircraft usage are mounted on the ship and help to defend it against any potential threats. The ship also features specialized aircraft, such as the F-4 Phantom and F-14 Tomcat jets, designed to intercept enemy aircraft and eliminate any they come across. Slower A-6 and A-7 Corsair bombers are also installed on the carrier to pound any surface targets. All Nimitz-class carriers are scheduled to be replaced by the Gerald R. Ford-class next-generation aircraft carriers when they reach the end of their deployments. The USS Gerald R. Ford can be referred to as the primary example of naval innovations, having much more advanced technologies than its predecessors, like seamless aircraft launch and recovery capabilities. Its automation and island structure boost efficiency and visibility, and is essential to provide additional benefits for operational situations. The USS Gerald R. Ford is a testament to American maritime superiority, merging cutting-edge technology with strategic prowess and navigating global challenges and shaping the future of naval warfare. You might be wondering, why is it necessary for such a massive and powerful aircraft carrier to be able to make high-speed maneuvers? Yes, high-speed turns and maneuvers are executed by numerous vehicles and vessels and actually fulfill many roles. In the case of naval operations, the United States aircraft carrier, the Gerald R. Ford, and its counterparts utilize their high-speed turning capabilities as a dynamic and strategic element. Understanding the reason behind executing such maneuvers involves diving deep into the military and practical aspects and exploring how these turns can contribute to the safety, effectiveness, and overall efficiency of naval operations. Evading enemies is a primary motive for executing high-speed turns in naval war scenarios. The ability to quickly change direction at high speeds can be helpful in avoiding potential threats in a hostile environment. These Navy-operated vessels, including the USS Gerald R. Ford, are assets that attract the adversary seeking to disrupt and neutralize their capabilities. By executing high-speed maneuvers, these vessels can catch the adversaries off guard and introduce an element of unpredictability among them, making it very difficult for them to accurately target and attack. Furthermore, these turns can also play a major role in dodging fierce and hazardous weather. Adverse conditions, including storms, hurricanes, turbulent speeds, high waves, or the potential for rogue waves, could cause significant damage to maritime operations, and in such scenarios, high-speed turns allow the vessel to navigate through or around the hazardous weather more effectively. So, how is all of this done on such a massive vessel? Making a high-speed turn on an aircraft carrier, exemplified by the USS Gerald R. Ford, involves a meticulous sequence of actions by the ship's crew. The captain's pivotal role unfolds as they issue a decisive order transmitted through the carrier's intricate communication system. This command triggers a swift response in the engineering spaces, where signals are dispatched to engineers responsible for managing the carrier's formidable power source, its nuclear reactors. In response, these engineers deftly adjust the control systems, orchestrating an increase in the vessel's power output. Concurrently, deep within the carrier's hull, technicians in the engine room closely monitor an array of gauges. Their hunting eyes track critical parameters such as temperature and pressure as turbines spin rapidly, ensuring the carrier operates within optimal ranges during the high-speed turn. Also, bear in mind that the mechanics of the high-speed turn extend to the carrier's propulsion system, where the propeller shafts play a pivotal role in translating increased power into dynamic motion. As the USS Gerald R. Ford executes the high-speed turn, it becomes a testament to the collaborative efforts of its crew, navigating the seas with a harmonious fusion of power, precision, and technological prowess. Now we'll look into a test that's conducted on every vessel commissioned by the United States Navy. This test is known as the Extreme Rudder Test. The Extreme Rudder Test is a critical evaluation of the life of a vessel operated by the Navy. In this test, the vessel undergoes rigorous and extensive testing for examination to ensure the utmost reliability and maneuverability of its rudder system. This test is a meticulous and controlled procedure designed to push the vessel's rudder to its operational limits, verifying its performance under extreme conditions. Conducted for various strategic and safety reasons, the Extreme Rudder Test provides invaluable insights into a ship's handling capabilities, responsiveness, and overall operability. One of the main objectives of the Extreme Rudder Test is to ensure that the vessel can navigate safely and effectively in areas of high seas. In emergencies, such as evasive maneuvers or a sudden change of course to evade any potential threats, the rudder becomes an essential component in steering the ship. Conducting this test enables the naval engineers and operators to evaluate and validate the reliability, suitability, and responsiveness of the rudder system, guaranteeing that it can swiftly and precisely execute adjustments even under extreme conditions. Furthermore, the test also helps in determining the overall worthiness of the ship. Sea conditions can vary significantly from calm waters to much higher waves in turbulent seas, and the vessel should be equipped with the capability to withstand these harsh environments. By subjecting the rudder to extreme angles, the test stimulates very difficult and challenging conditions, offering a small glimpse into how well the ship can navigate and stay stable in diverse conditions. This evaluation of the vessel is very important as it ensures that they can operate effectively in a wide array of missions and deal with any situations that they may encounter during their deployments. The Extreme Rudder Test also plays a vital role in the evaluation of a ship's design and engineering. Modern naval vessels, including aircraft carriers like the USS Gerald R. Ford, are feats of engineering marvels, incorporating advanced technologies and intricate systems. Assessing the rudder's performance under extreme conditions provides valuable data on the vessel's design integrity and the effectiveness of its propulsion and steering systems. Engineers can use the insights gained from these tests to refine and enhance future designs, continually pushing the boundaries of naval technology. Crew training and safety measures are fundamental pillars within the operational fabric of the USS Gerald R. Ford, one of the most advanced carriers in naval service. The crew undergoes a series of meticulously designed drills aimed at honing their skills and responding effectively during rapid turns, simulating scenarios that mirror the intense conditions of high-stress maneuvers. These drills, spanning various compartments from the flight deck to the engine rooms, give a sense of preparedness and adaptability that's vital for the carrier's operational success. On the flight deck, where precision is paramount in aircraft launch and recovery operations, crew members practice handling the challenges posed by dynamic maneuvers. In the engine rooms, the beating heart of the carrier's propulsion systems, crew members engage in drills that simulate the increased demands on machinery during high-speed maneuvers. These exercises highlight the importance of teamwork and efficiency, ensuring that the intricate systems below the deck can simply respond to the demands imposed by rapid turns. Technicians monitor gauges, make real-time adjustments, and collaborate with other crew members to guarantee the carrier's propulsion remains reliable and robust. Further, beyond the manpower, the USS Gerald R. Ford comes equipped with a wide array of advanced controls that are strategically designed to prevent overstress and instability on the ship's structure and safeguard against blackout conditions. These controls, intricately integrated from the bridge to the engine rooms, employ cutting-edge technology to monitor stress levels and regulate acceleration, ensuring that the forces acting on the carrier and its crew remain within safe limits during dynamic maneuvers. As the USS Gerald R. Ford continues to push the boundaries of naval capabilities, this blend of human expertise and technological innovation remains integral to its operational ethos. It ensures that the carrier can navigate the sea not only with cutting-edge technology, but also with highly skilled and safety-conscious crew, standing on its position as a flagship in modern naval operations. And this brings us to the end of our video for today. If you enjoyed it, then please make sure to hit that like button and subscribe to the channel with the bell notification on, so you're notified as soon as we drop more exciting content. Your support means the world to us and keeps us going to keep digging deeper and make more videos for you on all of these exciting topics related to the Navy. Thanks for tuning in. We'll catch you next time.